Hey everybody, this video lesson is going to cover the topic known as states of matter. First of all, what does state mean? Well, if you're talking about a state of a human being, they're usually talking about the personality of that person. Like, are they feeling good? Are they feeling sad? Are they depressed? Are they happy? Are they energetic? The state of a human is basically its personality or how it's feeling. The state of matter means how the matter is feeling. Now, matter obviously is not alive, so we don't know how it's truly feeling. But we could take a closer look at what the particles are doing, and we could take a closer look at the matter itself to identify what state it's in. If you're tired, you're probably in a sleepy state. If you're energetic, you're probably in an awake state. Well, matter has states as well. Chances are this is not the first time you've heard of the concept known as states of matter. You've probably been talking about this for a long time in your science courses, dating back to elementary school science. But every time we come back to this concept known as states of matter, you probably learn a little bit more and a little bit more about it. And so we're just going to first establish the basics and then build upon that. By the end of this video lesson, you'll be able to describe the three states of matter and put them in order or identify them based on the movement of the particles, the volume of the state of matter, in other words, how much space it takes up, the shape of the state of matter, and finally, the energy of the particles that make up the state of matter. What you're looking at now is a little slide from a PowerPoint that I used to do, but I will put a copy of this PowerPoint slide into our Schoology folder so that you can put it into your notes. That way you don't have to recreate the pictures. But we're basically going to take this slide and fill in the blanks and help establish those four things that we talked about on the last slide. The first thing that we're going to do is in these boxes, establish what the particle model looks like for each of the states of matter. You'll see solid, liquid, gas, and then inevitably every year some student asks about plasma. And so we'll address a couple of questions that have to do with plasma, which is essentially a superheated gas. Think lightning or even the surface of the sun. The sun looks like it's solid, but it's actually a superheated gas known as a plasma. Now you may remember from a previous science course that solids have particles that are very tightly packed together. So if you draw a particle representation in the box, you put little circles that have very little to no space between them. I put 2 rows of particles for that solid in the box, but you get the picture. When you look, there may be a little bit of pocket of space between the particles, but not much, and the particles are very tightly packed together. Next, in a liquid, you get the particles and they're not so tightly packed together. And as you know, liquids have this characteristic known as flow. It's a fluid. It can be poured out of a glass or poured out of a container or poured out of a faucet if it is water. And so the particles have a little bit more freedom of movement, and so the particles aren't quite as tightly packed together. So you can see in my picture now that I have 2 rows once again of particles, but you can see the pockets of space are much larger. With gas, you'll see lots of empty space between the particles. So if I were to represent the particles of a gas, you would see that there's huge pockets of space between the particles. In fact, most of a gas is empty space. The gas you're living in right now, the atmosphere, there are particles, and you know the particles exist because as the wind blows, you can feel it blow against you. It'll move your hair around, it'll move your clothes if it's blowing hard enough. But it's not a ton of particles, so you feel the particles hit you, but there's, for the most part, empty space, which is why you can see through it, because there's not much there. Finally, plasma. The particles are also very spread out, but they're also super fast moving. So I'll put a couple particles in the box to show the speed. You see the 3 lines there representing the speed lines. That's how fast they're moving. Pachoo! Flipping around that box as fast as they can. So let's go down to the next line when we talk about the movement. We're going to fill in the blanks here for solid, liquid, and gas. Let's first establish something that is true of all matter. All matter is always in motion. It may not look like the particles are moving in something, but I can guarantee you that if you were to shrink down on the size of an atom or a molecule, you would see that the particles are moving even a little bit. So when we talk about the movement of solids, liquids, and gases, let's first start with solids. Now, because the particles are tightly packed together, they aren't moving very much. In fact, they're probably just wiggling in place. Since we can't see at the particle level, we can't see this wiggling. But trust me, that desk you're sitting in, that table you're sitting at, your iPad that you're looking at or your phone, that's solid. Those particles are wiggling in place. Now, I already talked about this a little bit. The particles of a liquid have the ability to flow past one another, so they have a little bit more freedom of movement. So the particles slide past one another. And something else that's cool about liquid particles is that if you were down on the particle view, you could see the molecules and they could actually spin in place. They can rotate and turn. Solid particles don't rotate and turn. They're kind of locked in place and they just wiggle. But liquids can spin, rotate, and turn. They have freedom to move, freedom to flow. But in a liquid, the particles are still restricted a little bit in their movements. Let's move on to gases. In a gas, there is no restriction in movement, and the gas particles can move freely wherever they want. And so, when you look at the particles, they're bouncing all over the container that they're being held in. Inside a balloon, and when you blow it up, the gas particles inside the balloon are moving freely in any direction at any point that they want. They're colliding, they're moving. There is no restrictions. You can kind of think about particles in this case as students in school. Currently, we are in our COVID protocols, and so the solids can't move very much. Well, the students have to sit in their chairs and they can't interact with one another. Now, in normal school year situations, you have students that can move freely throughout the room, and so they can flow past one another, but for the most part, they stay within the room. And if there was no teacher around, maybe the teacher's sick and there is a sub that day, this is more like what the students would be like when there's little supervision, like when a sub's around. They can go in and out of the room. There really is nobody to tell them to stop moving and sit in their chair because students think they can do whatever they want. But you can't, so sit down. Just kidding, that's a joke. Let's now talk about the shape of the states of matter. So when you look at a solid sample, what shape does it take? Well, the question is, does it have a definite shape or does the shape vary? In other words, does the shape stay or does the shape change? Well, for solids, because the particles have very little movement and they just wiggle in place, they have a definite shape. Whereas liquids, if you pour a liquid into a different size cup, the liquid will take the shape of the container it's in. So sometimes if your cup is long and skinny, well then your liquid is long and skinny. But if you pour that liquid into maybe a short stocky cup, then the shape varies. And so we say that the shape varies for liquids. Now with gases, the same as liquids when it comes to shape. You can take a gas and move it into a different size container, and the shape of the gas changes with the container it's in. Plasma, likewise, would change depending on the shape of the container. If you could indeed contain a plasma, it would have variable shape. Let's talk about the volume of the different states of matter. And remember, volume is described as how much space the state of matter takes up. Solids take up a definite space. In other words, if you squeeze on a solid, it doesn't change how much space it takes up. You cannot compress or squeeze the volume of a solid. It has a definite volume. Now with liquids, also, if you squeeze on a liquid, it's not going to compress. If you've ever filled up a water balloon and you've got water inside the balloon and you put both hands around it and you try and squeeze it, now the water is going to try and escape out of the spots where you're not squeezing, but for the most part, if you're able to contain all the water in the palms of your hands and you squeeze on both sides, you can't make it get smaller. Like, it keeps its definite volume. And so we will say that liquids have a definite volume but a variable shape. Moving on to gases, their volume varies. And what I mean by that is that if you can take a gas and compress it into a smaller space, then it has a variable volume. The amount of space that that gas takes up changes. And maybe you've experienced this, like pumping up a bike tire or pumping up a car tire. You are basically forcing air from the outside of the tire and putting it into the tire. And so you're taking the air and you're compressing it and you're changing its volume. Or maybe you're a computer fan and you want to clean out your keyboard and you get that compressed air that you can buy at the store and you spray it inside your keyboard to blow out all the dust so that your keyboard works more properly. Compressed air. The fact that air can be compressed is evidence that it has variable volume. The same with plasma. Plasmas are like gases, they're just superheated, and so we say that the plasma also has variable shape and variable volume. Now the last thing that I want to add into the bottom of this slide, and you'll have to add this in manually because that's what I'm doing as well, is discussing the energy of the particles. And energy is proportional to temperature. And what I mean by that is that the energy of the particles goes up as the temperature of the particles goes up. So if you warm up a piece of solid and get it warmer, the particles are going to have more energy. They're also going to wiggle in place, but a little bit faster. You've maybe experienced this when you've seen an ice cube melt and turn to a liquid. The way to get an ice cube to turn to a liquid is to heat it up, and the energy of the particles increases. Eventually, all those solid particles turn to liquid, and then you now have liquid. But the reason that the solid turn to a liquid is because the particles have more energy. So we're going to use just words to describe the energy of the particles. And we'll say that solids have low energy. And you can relate to this. If you have low energy because you just ran 3 miles or something, you probably want to just lie on the couch and not do anything. You have low energy, and so you are very static. You stay in place. You don't move very much. So solids are the same way. They have low energy, so they just stay in place. Now liquids, on the other hand, we'll say have medium energy. Their particles are moving at a medium speed. They have freedom to flow a little bit, and so their energy is kind of in the middle. Gases, on the other hand, are considered to be high energy particles, and so we'll say these are high. And plasma are very high. Now you can imagine the different types of questions that I could ask on a quiz or a test or even on some homework problems. Maybe I give you just a state of matter and describe it. I'll say it has like, the state of matter Mr. Calmy is holding has freedom to flow with variable shape and a definite volume. What state of matter is Mr. Calmy trying to describe? And you would say, oh, that sounds like a liquid. Or maybe I would do some sort of question where I say, put these states of matter in order of energy from lowest to highest, and say, okay, well, the lowest energy would be solid, the medium energy would be liquid, and the highest would be gas. And the very highest would be, of course, plasma. So I could do an ordering question like that, or I could describe a state of matter and ask you what state of matter it is, or I could say, describe gases in their movement, shape, and volume, and you'd have to describe them precisely how they move, how they have freedom to move anywhere, with variable volume and variable shape. So these are the types of questions that I would expect you to be able to answer now that you know a little bit more about the states of matter. Well, that takes care of this video lesson. Thanks for watching.